Right, well, I hope you all had a nice break yesterday and a nice Easter weekend. So in Britain, at least for the schools, so for high schools and primary schools, we get 2 weeks holiday for Easter. So it always in Slovenia seems a bit of a shock to only have 1 day of holiday for children, especially. But in any case, I hope you all had a nice weekend, and now we missed the holiday this time in this course, but anyway, we'll carry on. And this is an interesting point in the course, because from next week we're going to begin studying arithmetic, the theory of the logical theory of the natural numbers. And we're going to do that because we're going to start the material on Gödel's theorem. And Gödel's theorems, in fact, there are going to be 2 theorems, Gödel's first incompleteness theorem and Gödel's second incompleteness theorem. And that's going to take us 4 weeks of lectures to get. So in the 3rd week of the lectures starting from next week, 3 weeks after next week, we'll do the first incompleteness theorem, and the week after the second incompleteness theorem. Up to now, the recent lectures we've been doing model theory. Today is going to be a sort of transitional lecture, taking us from model theory, but connecting with some concepts that are going to be very important when we do Gödel's theorem, particularly regarding axiomatizations of theories. But the goal today we're going to see its relevance to Gödel's theorem, to Gödel's theorems in due course. The goal today is to use model theory for a practical purpose, and that purpose is to get some decidability results. So again, to show that logical theories are, so certain interesting logical theories are decidable. So we want a title for the lecture. This one's going to be called Decidability, or this one can be called Decidability via Model Theory. So from the point of view of this lecture, the interesting material, or the interesting purpose of the lecture, is to apply model theory to get some results, so decidability results. But from the viewpoint of the future of the course, going into Gödel's theorems, actually the most relevant parts of the lecture are going to be issues to do with axiomatizations of theories, which we'll come to when we get to them today. So I want to look at decidability. We've already several times in this course proved that theories are decidable, particularly in I think the 4th and 5th lectures when we were applying quantifier elimination. I don't want to be very rigorous about it today, about decidability. So if one wants to be mathematically precise about decidability, one needs to give a model of computation and make formal definitions about the model of computation. You basically need to define the notion of algorithm. And several people in this room did the Computability theory course last semester, and they will have already seen that. And for our purposes, we don't want to go into that level of detail in this course, but I do want to be a bit more specific than we've been so far, because we're going to be looking at decidability today. So I'm still going to keep the notion of algorithm informal, but let me clarify a bit the sort of thing that an algorithm does. So we're going to consider algorithms. And by algorithm, you can think computer program, if you like, taking what one might call discrete data, or let's say working with, because I was going to say taking discrete data as input, but we're also going to be interested in the output. So working with what one might call discrete data. The discrete data means data that we can give to an algorithm, say a computer, and it's discrete. So it's not like from continuous mathematics, it's from discrete mathematics, which makes it easier to code it up as bits, if you like, as binary digits to give it to a computer. So examples of discrete data are things like Booleans, true and false, natural numbers, let's say sequences of natural numbers, finite sequences of natural numbers. And also more complicated kinds of things that are relevant to logic. So if we give ourselves a countable signature, then the terms over a countable signature can also be encoded as discrete data. You can sort of imagine coding them up so you could input the terms to a computer. And we'll say terms over a countable signature. Just as we can encode terms, we can also encode formulas, so logical formulas. Over a countable signature. And if we can encode formulas, and we can pass formulas as inputs to an algorithm, so just as we have finite sequences of natural numbers, we have finite sequences of formulas, and we have a very important application of finite sequences of formulas in this course, namely the proofs in our Hilbert system. They're finite sequences of formulas. So we can perfectly well give formal proofs as inputs to an algorithm, or expect to get them as outputs from an algorithm. So formal proofs in our Hilbert system. And these are totally non-exhaustive, so there are many other kinds of discrete data that one might give as input to algorithms or as output from algorithms. So I want to revisit the notion of decidability, so what it means for a collection of things to be decidable. So in order to do this in sort of nice general form, let's suppose D is a collection, or let's say a kind of discrete data. So it could be the set of Booleans, or the set of natural numbers, or the set of sequences of formulas, or something like that. Then we say a subset S of D is decidable, and I've already given an informal definition before, and this is again an informal definition because I'm going to use an informal notion of algorithm. So only the difference with what we had before is that I'm now being a little bit more precise about what kinds of data, what kinds of sets I'm considering, so namely sets of some kind of subsets of some kind of discrete data. So for example, this might be the set of all logical sentences, all sentences over some fixed signature we've got, and we're looking at whether a particular set of sentences is decidable. So like a theory, for example, would be a set of sentences over, if this was the set of all sentences, and then we have some subset of sentences, and it's decidable as before if there exists some algorithm we can think, which, if you don't know the formal definition of models of computation, just think of this as some precise set of instructions that tell us how to compute with it, or if you like, a computer program. There exists an algorithm that takes any element of the set of data items. So D is the set of data items, any element little d of the set of data items D as input and returns output. So yes, if D belongs to the subset S, and no, if D does not belong to the subset S. And the really important point here is that the requirement is that for every where is it? For every data item that we're considering, little d, from the set of all the data items, for example, set of all formulas, for every such element, eventually the algorithm will go and compute for some time, but eventually you get the correct answer. So eventually you either get yes or you get no. You may have to wait a long time, but eventually you wait long enough, patient enough, you will eventually get an answer. So NB, nota bene, note well, means that the algorithm is required to terminate that's eventually return an answer. Well, let's make this even clearer. It doesn't just terminate and get stuck here to eventually return an answer for every element of our kind of data we're considering as inputs. Okay, so that's the notion of decidable. That definition should be consistent with what we've already done before. There's a weaker notion, which is also very important, and this is called semidecidable, and it's basically very similar, only you get less information. You only get the positive information, but you don't get the negative information. So how do we formulate that? Well, let's maybe a subset S of D is semidecidable. Again, if there is an algorithm, just say there is an algorithm that takes any element of the kind of data we're considering as input, and then I can't say returns as output because we require that it returns an output in the case that D belongs to the set S. So returns yes as output if D belongs to the subset S. But in the case that we give it an input that does not belong to the subset S, we don't require any output. The algorithm is just allowed to keep on computing forever. And in fact, we can say it has to keep on computing forever. That gives us a nice tidy definition. So it computes forever without, so forever is all one word, forever without returning an output. Any output if D does not belong to the set S. And this is what I'm about to say is going to foreshadow some things that are going to come, but it will hopefully give you an intuition for why this is relevant. So, for example, we might consider looking at, we've got the set, D is the set of all sentences, and we want to consider the set of all sentences that are logically valid. We know that being logically valid means being true in all structures, but we also know by soundness and completeness that logically valid is the same as having a proof in the Hilbert system. So we might imagine we want to test if a given input sentence is logically valid. That's a useful thing to do. Now, is this a logically valid sentence or not? It's a useful thing to do. And in fact, it's not that hard to see. We can give a what's called a semi-decision procedure for this. It's not that hard to see it's semi-decidable. Because what we do, if it's logically valid, there exists some proof of it. And the proof is a finite sequence of formulas following certain rules. And actually, finite sequences, there are only countably many formulas, there are only countably many finite sequences of formulas. We can systematically enumerate all the finite sequences of formulas, look at them, and check whether each one's a proof, whether it follows the rules of the proof system. And so if we've got an input sentence A, and we want to see if it's logically valid, we go through every finite sequence of formulas in turn, one at a time, and look to see if we have one that is a proof whose conclusion is A. And if so, then we found a proof of A and we return yes. Of course, if it's not a logically valid formula, we will never find such a proof, but we'll never know that we haven't, we'll never know to stop the search, because we might just have not yet found the right proof for it. So the algorithm I've described is an algorithm that will return yes if a formula is logically valid, and will compute forever if the formula is not logically valid. So, we'll do this in more formality at some point later in the course, maybe even today, I can't quite remember. Anyway, that's an example of a semi-decision procedure that gives you the idea of why this is natural that sometimes we can return yes if we have an element of the set, if we're doing some search, but we can't return no because we never quite know if we've searched far enough. We don't know if we've not found the thing we're searching for yet. We never know. We don't know when to stop the search. Anyway, so apologies for people that took the Computability theory course. This is now this stuff that was very much core to that course. So I am going to need to go over a few basic results relating to decidable and semi-decidability. Let me remind myself what we need to do. So for the purposes of this course, we don't need to go into it in that much detail, but we do need the following, I should say, proposition. We do need the following proposition, which is, firstly, every finite set. So you've got a finite subset of your set of data items, every finite subset is decidable. And that's easy. We need to give an algorithm that will return yes if you belong to a finite set, or no if the input does not belong to the finite set. It's just, for those of you who know programming, it's just a big case statement, if you like, or a big if then else statement. So we've got the set maybe contains k things, x1 up to xn, xk. So you just check if your input equals x1. If so, you say yes. If not, then you check if it equals x2. If so, you say yes. If not, and you keep on doing that until you get through to xk. Once you've compared it to all x1 to xk, and if it's failed to equal any of them, you say no. So it's very easy to give a decision procedure, as it's called, namely an algorithm that will return yes or no in this case. So finite subsets are always decidable, but they are not the only sets that are decidable. So there exist, just to comment, there exist infinite decidable sets. infinite decidable. For example, the set of even numbers is an infinite decidable set. Given an input number, you can check infinitely many steps if it's even. You know, if you've got it represented in in binary representation, you just look at the rightmost bit and see if that's 0, basically. Or an even easier infinite decidable set is just the set of all natural numbers itself as a subset of, if you're having inputs natural numbers, then you just simply return true, because every number belongs to the set. So you simply return yes. So thirdly, being decidable is a stronger property than being semi-decidable. So every decidable subset S is also semi-decidable. And that's easy. Well, if you've got a decision procedure, an algorithm that will return yes or no, we want to give instead a semi-decision procedure, or we simply run our decision procedure, and if it says no, we just augment the algorithm by saying, well, if our original algorithm says no, we just go into a little loop and we hide that information from the user. And we're giving an algorithm that's, yes, less useful than the original one, but never mind, it tells us that every decidable subset S is semi-decidable. But the converse doesn't hold, which is why we need the separation. So there exists semi-decidable sets S that are not decidable. Okay, so I gave you some intuition for why the other three hold. The first three, we might just say, I've kind of talked you through the reasons. These are easy. This is a deeper result, and this is sort of the result where computability theory really gets started. So this is a result by Church and Turing. A very famous example of such a semi-decidable set is what's called the halting set. So essentially, you have a computer program. The question, does it halt on some input? Does it actually terminate on some input, some given input? That's something that you can show is a semi-decidable set, but not a decidable set. The set of programs for which it terminates, but the set of programs that terminate on some given input is a semi-decidable set, but not a decidable set. But the proof of that would require an hour and a half of lectures or something, so we're not going to do that. What's more relevant for us today is the following result. And this is something that we're going to apply a couple of times. So this is something we can prove, which is that decidability and semi-decidability have quite a tight relationship. So to establish that a set is decidable, it's not enough to establish that it's semi-decidable, but it is enough to establish that both it and its complement are semi-decidable. And in fact, that's equivalent to decidability. So a set is decidable, the subset S of our collection of data is decidable if and only if S and its complement are both decidable. So proposition S, a subset of D, is decidable if and only if both S and complement of S, but that's everything in D that doesn't belong to S are semi-decidable. The one direction of this, like this pen. So one direction of this is easy. If a set is decidable, well, we already saw that decidable implies semi-decidable. It's easy that decidable implies the complement is decidable. So basically the left to right implication is easy. And also follows from the previous observation that decidable implies semi-decidable. So the converse is the interesting thing. The converse is, suppose S and S complement are both semi-decidable. So from the point of view of this lecture, what this means is we've got semi-decision procedures, so algorithms, that we've got two of them. One that will return yes on any input that belongs to S, and a different one that will return yes on any input that belongs to the complement of S. And both of them will never return negative information, but that doesn't matter. The idea is simply we want an algorithm that, given an element of D, will any element little d of D will always terminate. The algorithm is the idea is we can essentially run these two semi-decision procedures in parallel on little d, and one of them will eventually terminate. We wait to see which one terminates, and we might run one in one room and another in a different room so that we know which one's which. And we go back and forth between the two rooms, and we wait to see if one of them terminates. And when only one of them will terminate, because little d can only belong to one of the two sets, and when one of them terminates, we know which answer to give. So the rough idea is, let A be an algorithm that semi-decides S, and let B be an algorithm that semi-decides S complement. Run A and B in parallel on our input D. If A returns yes, then that means that the element D belongs to S, so we return yes. And if B returns yes, then the element D belongs to the complement of S, so we return no. So if A returns yes, then by we I mean our algorithm that we're describing that's a decision procedure, then we return yes too. And if B returns yes, and only one of these can happen because little d belongs to exactly one of S and S complement, then we return no. Okay. If you don't like doing things in parallel, then you can do one step of the algorithm A and one step of the algorithm B, and so on, do what's called interleave the algorithms. Depends on what you want your notion of algorithm to be. But it doesn't matter, whatever you have for your notion of algorithm, this result is going to be true. Okay. So I want to do one more result about computability from this informal perspective. So the whole point here is to introduce you to these concepts. Some of you did the computability theory course, so you know them well already. But for the point of view of this course, I want to have these concepts described from it's a sufficient level of detail that we can work with them, but sufficiently informally that we don't get too tied up with exactly what the definition of algorithm is at the moment. The last thing I want to do is just mention a result about semi-decidable sets that characterizes them. So let's call this a theorem. That's what my notes say. So the following are equivalent for S for a subset S of D. So the first one is S is semi-decidable. But before going into the other points, I want to motivate it. So what I've been considering so far is the idea of being able to, so both decidability and semi-decidability concern the idea of being able to test an element, some input element, little d, in order to see whether it belongs to a set S. Okay, so we're looking at testing membership of the set S. In the case of decidability, we get full information. We get both positive and negative information, depending on whether little d belongs to S or not. In the case of semi-decidability, we only get half the information. We only get the positive information. But still, we're testing whether an element belongs to the set S. Another important thing one wants to do with sets is to generate them or enumerate them. So rather than testing an element, if an element belongs to a set, it's a useful thing to know if we've got a set, if we've got a systematic way of listing all the elements. Of course, it might be an infinite set, so you might need an algorithm that will run forever, but still an algorithm that will systematically list all the elements of S. And it turns out that sets are systematically listable if and only if they're semi-decidable. So that's a relatively, it's not completely trivial. I'm going to skip one of my statements here. So I'm just going to put, in fact, I'm going to skip two of them. The following are equivalent for a set S. So it's semi-decidable, or we have a way of enumerating as an infinite sequence by an algorithm that will return one data item as the first item, another data item as the second item, another one as the third item. We have such an algorithm that will systematically enumerate all the elements of S. Of course, it can't do that in the case that S is the empty set. And the empty set is semi-decidable because it's actually decidable. I mean, it's semi-decidable. The semi-decision procedure is just an algorithm that goes immediately into a loop, whatever input you give it, because no element belongs to the set. So the empty set is semi-decidable. We can't enumerate its elements as a list because it doesn't have any elements. So if S is semi-decidable, the equivalent thing is that S is either going to be the empty set, or S is what's called computably enumerable. I.e., there exists an algorithm that takes. Well, you can imagine there are two ways of imagining it. One as an algorithm that runs forever and keeps on printing out an output item, so it's printing out an infinite list of items, And the point is that the set S is going to be the set of all the items that appear on this list. Or another way of thinking of it is we can give it a number as input and it will return. So it's like a function. We give it a number as input and it will return the nth item on the list. So I'll write it in that way. So that takes a number n and as input and returns an output, let's say little s, that's a small s, little s belonging to D, a set of data items D, such that, so satisfying every, actually, let's just put it, I was going to say every Sn belongs to S, but why don't I just say Sn belongs to S here? So the point is, we give it a number n, we say, give me the 115th element according to the choice of ordering that you've got. Give me the 115th element of the set S, and it gives me back this. But the requirement is that every element of S occurs at least once in this listing. Okay? So such that for every S belonging to S, there exists a natural number, such that again, S is such that S is the element S of n. Okay, so in other words, i.e. S0, S1, S2, S3, S4, S5, S6, and so on, is an enumeration of the set S. And that every element of S will appear somewhere in this listing, but possibly with repetitions. Well, it's actually also possible to eliminate the repetitions, but let's not worry about that. So possibly with repetitions. Okay, so in the LaTeX lecture notes, there's a bit of a proof of this. For those of you who did the computability theory course, you will have seen the proof already. I don't want to spend lecture time on a proof of this. The proof of this is not examinable material for this course. This is computability theory. But just to say, it affects the terminology in the sense that we've got two different ways of looking at semi-decidable sets. The testing way, as I said, can we test in a positive way for membership of the set S, or the listing way, can we list the elements of the set S? Both are equivalent, but there's terminology for the semi-decidable sets that emphasizes these two different ways of looking at them. So we can call semi-decidable sets semi-decidable. We can also call them computably enumerable. And it doesn't matter. I mean, computable enumerability is used as a synonym for semi-decidability. So we also say the empty set is computably enumerable. So terminology. So terminology, we have semi-decidable. So semi-decidable set. The synonym for that is computably enumerable. So to give this idea that we can, so it conveys a different idea, namely that we can list the elements of the set, but it's the same thing. That abbreviate C.E. Well, there's an older terminology that people still use sometimes, which is recursively enumerable, or RE. And decidability has also other synonyms. So we have decidable set,
is also called a computable set, which is also called a recursive set. And on the whole, I think I shall today at least use the semi-decidable and decidable terminology. Okay, so that's a review in this first part of the lecture of concepts relating to decidability and semi-decidability, as we're going to need them for the moment for the rest of the lecture today. Very slightly early, but it's a good pausing point. So is now we switch to logic. And okay, so I make it 58, so we'll start again at 13 minutes past 9. Okay, so the goal of looking at these concepts from computability theory, the notion of decidable and semi-decidable set and the various properties of them, from the purposes of logic is twofold. One is that, as we've already seen in the course, the notion of a theory being decidable is an important one in logic, because it's useful to have algorithms to be able to decide whether or not a sentence belongs to a theory. But the other purpose, which is new from this point on, is that something else that's often very important to get a handle on a theory is to have an axiomatization for a theory. And the notions of computability, of decidability and semi-decidability turn out to be very important with regard to what kind of axiomatizations one can provide for a theory. So I now want to look in this part of the lecture on the property of, on the notion of axiomatization. So axiomatized, if I was American, I would write that with a Z. And I would actually say that I was writing it with a Z rather than a Z. But anyway, I'm not American, as you know. So anyway, we're going to look at axiomatizations. And the idea of axiomatizations, as I motivated, if you can remember, in the second lecture, when we were on sort of introductory material to the course, the idea of the axiomatization of an axiomatization is to be able to present a theory in terms of some ideally axioms one can sort of nicely list or nicely describe in a sort of simple, straightforward way. But in general, we often present a theory, and we often present a theory P via an axiomatization S. So in other words, an axiomatization has a set of axioms, so i.e. S, so i.e. let's not put this in brackets because this is important, i.e. S is a set of sentences, necessarily a subset of T, which will follow from the next thing, and T is a theory which is all the logical consequences of the axioms in S. So T is the set of those sentences A, such that A is a logical consequence of. So I think we might have also had, this notation in lecture 2. But anyway, the point is we found a set of sentences S such that it axiomatizes the theory T. So everything in T is a logical consequence of the set of sentences S. Now the thing about axiomatizations is it's often an interesting question, can we provide a nice set of axioms for a theory? So one nice set of axioms, one notion of niceness for a set of axioms would be a finite set of axioms. Can we give finite axiomatization of a theory? So actually, when we start looking next week at the work leading up to Gödel's theorem, actually in 2 weeks' time, we're going to be looking at axiomatizations of the natural numbers. And those axiomatizations, the interesting ones, are not finite axiomatizations. So we can't, we're often in a situation that we can't give a finite set of axioms for a theory. So the next best thing, if we can't give a finite set of axioms, would be to have a set of axioms that we can at least recognize in some strong sense. So a very nice property to have would be that the set of axioms is decidable. So at least if we're given a sentence, we want to check if our sentence is an axiom, we've got some decision procedure we can apply which will tell us whether or not the candidate sentence is actually an axiom. So decidability is like we can recognize axioms and non-axioms, or a weaker property would be if we've got a semi-decidable set of axioms, then we can recognize the axioms, but we can't recognize the non-axioms. But on the other hand, one thing we can do if we've got a semi-decidable set of axioms is we can enumerate them all in a list. So at least we can, if we've got a semi-decidable set of axioms, we can at least find a computer program that will list the axioms one by one, even though there are infinitely many, it will eventually list every axiom. So these are the kind of considerations you want to consider about axioms. It will turn out that, for example, in the case of the theories for the natural numbers, we're going to consider piano arithmetic, a very standard axiomatization of the natural numbers. That does not have a finite axiomatization. You might say, but that's strange. I remember seeing finitely many axioms for piano arithmetic. Well, it turns out the induction axiom, as it's called, is actually an axiom schema when you write it in first order logic. So the induction axiom is actually infinitely many axioms. So that's, but obviously there's a pattern to the induction axiom. And indeed one can recognize if a sentence is an axiom of piano arithmetic or not. So the sentence in piano arithmetic is axiomatizable by a decidable set of axioms. On the other hand, what one might call the truths of arithmetic, namely those sentences that are true about the natural numbers, that's an axiomatization, but it turns out to be one that's not decidable or not even semi-decidable. That's a very an axiomatization we can't get our hands on. So anyway, we motivated it. We're going to have a couple of definitions. So actually, although I said I was going to use the decidability, semi-decidability terminology, in the case of axiomatizations, it's traditional to use the computable, enumerable terminology. So to stick with standard terminology, so we say that a theory T is computably axiomatizable if there exists a computable S that axiomatizes T. So I didn't actually write it down, but this part here, this is a definition of S axiomatizes T. Or S is a set of axioms for T. Okay, and we say that T is computably enumerably axiomatizable. Enumerably axiomatizable. If there is, so let's put the bits we're changing. If there is a computably enumerable S that axiomatizes T. So I'll just change the relevant bits. Steve green, it doesn't really matter. but these replace the green bubbles. Let's put some ditto marks in. Okay. So kind of the nice notions of a theory being axiomatizable that we're going to have that are relevant for us are theory being finitely axiomatizable, which doesn't need any discussion. I don't need to give a definition of that. It's kind of obvious what it means. Theory being computably axiomatizable, and a theory being computably enumerably axiomatizable. Now, if you read the logic literature, you will find that the notion computably enumerably axiomatizable does not really occur in the logic literature, which is just as well because it's quite a mouthful to say it. But there's a reason that one doesn't really encounter it, and that's the following theorem, which is a little bit surprising, which is the following are equivalent. Or a theory T. I should say, by the way, I should have made this explicit. I'm always considering a countable signature here, because just to be able to talk about the notions of decidability or not, one needs to have data, have sentences that one can encode up as natural numbers. And if you don't have a countable signature, you're stuck. So anyway, I'm assuming a countable signature, our signatures will normally be finite anyway. So the following are equivalent. So that T is computably axiomatizable. It has a nice decidable axiomatization. So remember, computable means decidable, computably enumerable means semi-decidable. So maybe just the computable, decidable, computably enumerable, it's the same as semi-decidable, just to remind you. So having a nice computable axiomatization is the same thing, it turns out, as having a computably enumerable axiomatization. But T is, so fortunately, we won't need to say computably enumerably axiomatizable much more. So computably enumerably axiomatizable. And actually, this turns out to be the same thing as T itself as a set of sentences being itself computably enumerable. So T is computably enumerable. Once we've proved this, the relevant things in this course are going to be, sometimes we'll be approaching from the perspective of having an axiomatization, and the relevant thing is going to be having a computable axiomatization. Sometimes we'll be approaching from the perspective of looking at the whole theory T itself, and then the relevant concept is going to be that T is computably enumerable here, or T is semi-decidable. The notion of computably enumerably axiomatizable, we won't need to consider more once we've got this proof out of the way. So the proof I'm going to do, 3 implies 2, implies 1, implies 3. Go around in that circle. The reason for doing that, well, in fact, it's easy to show that either of the other two statements imply statement 2, but then the easiest circle to do is 3 implies 2, implies 1, implies 3. So firstly, 3 implies 2 is easy, because if T is computably enumerable, you can just simply take T as an axiomatization of itself. Okay, T is a theory, so we close it under consequences. Its consequences are exactly clear. Easy, take T as its own axiomatization. Okay, so 2 implies 1 is the most interesting step, so we'll do that next. So we've got a computably enumerable axiomatization, and this is the surprising step that 2 implies 1. We've got a computably enumerable axiomatization. We want to find a computable axiomatization. So we have, let S be a computably enumerable, I'm going to be very happy myself once this theorem's out of the way. A computably enumerable axiomatization. So I don't need to say all these long axiomatization. But S be a computably enumerable axiomatization. In other words, it's semi-decidable. So we have a semi-decision procedure for S, namely an algorithm that, given a sentence, will eventually say yes if the sentence belongs to S, but will never return any result if the sentence does not belong to S. So we have a semi-decision procedure. Semi-decision procedure S. And I'm just going to go ahead and define a computable axiomatization for the theory T. So the following decidable axiomatization, so hence computable, the following is a decidable axiomatization. C. So we're going to call it S prime, and it is the set of sentences where we're basically going to use the axioms in S, but we're going to attach to them sufficiently much additional information that it allows us, that the axiom itself contains enough information to allow us to decide whether or not A belongs to the axiomatization. So to do that, I mean, the way I do it is I add an or false as like a sort of end marker here. So this is equivalent to A. And then I put this in conjunction with true, with a conjunction of trues. So this whole sentence is logically equivalent to A, but I'm going to copy true K many times, where K is going to give us enough information to be able to decide that to tell that A belongs to know, to be able to decide that A belongs to S. And the point is, we have an algorithm that will semi-decide whether A belongs to S. So an algorithm is a number of steps. Well, when you execute it, it will execute a number of steps in time. It'll take a certain amount of time before, if it halts, it will halt in a finite amount of time. And what we're going to ask is that we add such an axiom in the case that A belongs to S, and the semi-decision procedure, the algorithm we have for semi-deciding if A belongs to S, the semi-decision procedure for S, well, for running up an input A, or on input A, halts with yes after exactly K steps. So this is decidable. This means S prime. Be clear. S prime is decidable. Right, let's see why that's the case. So this is the interesting thing now, and I'm not going to write it down, but should just be able to think about it and understand the reason once you've heard it once. But the reason is this: we want to decide S prime. So we're given an input sentence. We want to decide, does that input sentence, let's call it B, belong to S prime? So firstly, we check B, we simply look at it, and we see, does B look like A or bottom in brackets, followed by a conjunction of truths? If it doesn't, then it doesn't belong to S prime. If it does, we look at how many truths, so we extract the number K. So we say, yes, it does look like this. We extract the number K, and then we input A to our semi-decision procedure, and we run that semi-decision procedure for exactly K steps. If at the end of that, the semi-decision procedure outputs yes, then this sentence was in our axiomatization. If at the end the semi-decision procedure after exactly K steps doesn't output yes, then it's not in our axiomatization. So the point is, the very form of the axiom itself gives us a bound so that we can run the semi-decision procedure. And normally we don't know how long to run it for, but here we're giving ourselves the bound for how long we want to run it. So S prime is decidable, and it's absolutely clear that S prime is logically equivalent to S, because every sentence in S, there's some K, there's exactly one K, such that the axiom appears in this form in S prime. This is logically equivalent to A, and S prime is basically a copy of S, just with the axioms a little bit mutated, so to speak. S prime is decidable, and S prime axiomatizes the same theory as S. Okay, so that's 2 implies 1. So we now just need to do 1 implies 3. And this is the point at which I make, well, I'm going to reiterate something I said in the introduction to this lecture, only this time we'll write it on the board. So which direction do we need? 1 implies 3. So we suppose that T is computably axiomatizable, and we want to show that T is computably enumerable. So let S be a computable, that's decidable. Let me use the word decidable this time. A decidable axiomatization for T. And we want to implement a semi-decision procedure for T. So again, I'm just going to tell you what the semi-decision procedure is. The following is a semi-decision procedure for T. So remember, that T is the set of logical consequences of the set of our decidable set of sentences S. So how can we enumerate the set of logical consequences of S? Well, it's the same. Well, sorry. How can we decide if? Okay, so sorry. Let's go back. Is that we want a semi-decision procedure for T. So let B be an input sentence. And we want to find an algorithm which will tell us, will answer yes if B is a logical consequence of the set of sentences S. Now, to be a logical consequence of the set of sentences S is the same thing as having a proof in the Hilbert calculus that we did a few lectures ago from assumptions that all belong to the set of sentences S. So what we're going to do is we're going to, as I described it more informal, actually at the same level at the beginning of the lecture, we're going to enumerate all sequences of formulas. So consider to use an algorithm that enumerates as a long list. There are only countably many sequences of formulas that enumerates every sequence of formulas. And for each sequence, we first check that it's a proof in the Hilbert system, namely checking that every successive formula in the sequence follows one of the proof rules from previous formulas in the sequence, or is an assumption. So we check for each sequence, if the sequence is a proof in the Hilbert proof system, using assumptions, using only assumptions in S. So we check that our proof is following the rules, and whenever we have a formula that's just been introduced into the proof that's not a logical that doesn't follow, is not a conclusion of one of the rules previously, that formula needs to belong to the set S. And we can check if a formula belongs to the set S because it's decidable, okay, because the set S is decidable. So basically, we look at a sequence and we say, am I a proof? Do all my assumptions belong to the set S? And is my conclusion B? So here we're using the decidability of S. Of S. And as conclusion B. So basically, we're enumerating every sequence of formulas. For every sequence, we check this. And if at any point we find a sequence of formulas that is actually a proof, where all the assumptions were in S and the conclusion is B, we output yes. If the check ever succeeds, output yes. And that's the end of the proof. This is very, very inefficient. I mean, so you could actually consider a practical version of this, that we've got the axioms for Zermelo-Fraenkel set theory with choice. That's a decidable set of axioms in a signature that only has the membership. We could input to such a semi-decision procedure the statement of the Riemann hypothesis and let our computer program check all possible Hilbert proofs, starting using the axioms of ZFC, and go through the list of all such things and wait to see if it ever finds one with conclusion, the Riemann hypothesis. Probably a few such programs are actually running at the moment somewhere in the world, but at least as far as I know, none of them has ever come up with a proof. Though actually, I did hear a rumor that somebody is claiming to have proved the Riemann hypothesis at the moment. So, but I'm not sure the source is very reliable. So, anyway, never mind. Let's not get into sidetrack. Let's not get sidetracked by gossip. Yeah, I think it was probably misreporting this because it was actually a very well-respected mathematician. Right, so good. So we know that Computably axiomatized theories are the same as computably enumerably axiomatized theories, and that should really be the last time I ever need to say that, are the same as computable enumerable theories. So now I want to get finally to an example, and going to use some of these notions of theories, although actually having gone through these computable axiomatizations and stuff, I'm now going to actually consider a theory that has a finite axiomatization. So that's obviously a computable axiomatization, but it's but I want to consider two examples. So actually, both examples that have in the lecture have finite axiomatizations. But anyway, this is going to be very useful, this result, when we come to Gödel's theorem and number theory, because it's going to be important that the notion of at that point, the notion of computable axiomatization is going to be really important. So it's good to have got that out of the way. Right. So now we're going to consider. So now we switch gear and go to example mode. The rest of the lecture is going to be two main examples, introducing some logical techniques from model theory that allow us to prove decidability. So an example. In this case, finitely axiomatized theory, finitely axiomatizable, but that's, since I'm giving an axiom, an actual axiomatization, I'll call it a finitely axiomatized theory. And it's actually one you've considered before. And this is the theory called, logicians called DLO. As you've seen this before in an exercise class when we were doing quantifier elimination. This is the theory of what are called dense linear orders without endpoints. So it's a simple theory. It's got finitely many axioms, and I'm going to give them all. It has the signature as just one binary relation symbol. And we want this to be a strict order. So we have the axiom. So of course, this is really for all x. It's not true that x is less than x. So this is we're going to choose a strict order, but I'm not going to put the quantifiers in the other axioms, but it is a set of sentences. So we have the axioms for a strict linear order. So the transitivity axiom. The non-reflexivity, irreflexivity, the trichotomy axiom for a linear order, that any two x and y that are distinct from each other, one of them is below the other. Then, so this is strict linear order. So the strict here just means it's the irreflexivity part. The density says that if x is less than y, then there exists a z such that x is less than z and z is less than y. There's always a z between them, so this is density. And the no endpoints say there's no least element and no greatest element. So to say there's no least element for any x, there exists a y such that y is less than x. And so say there's no greatest element for any x, there exists a y such that x is less than y. Right, so 6 easy axioms. And you did quantifier elimination for this, so you know you already proved in whichever exercise class it was that this theory enjoys quantifier elimination and is indeed a complete theory and is decidable. So I'm going to just show how quantifier elimination, as you might remember, is a bit fiddly, lots of manipulations of formulas. So let's see how we can see this from a more informed mathematical perspective, one might say, using notions from model theory now. And one of the results we're going to use is actually going to involve computable axiomatizations, although in this case, the fact that it applies in this case is kind of trivial because this is a finite axiomatization. So I need to change the camera. So in an earlier exercise class, you saw DLO is complete, but enjoys quantifier elimination, quant LM, and is complete and decidable. At least I hope you did complete this. Sort of pulls out anyway. So here we give alternative proofs of completeness and decidability using model theory. So one of the main observations here, well, so actually there's going to be the use of model theory and then a general result applied to that. So actually we use model theory to prove completeness. And this is a really beautiful argument. But I think I might leave this part until after well, we'll see how we go. But we use model theory to prove completeness, and having established completeness, we're going to see that decidability then follows by a general result. And maybe I'll do this general result first. So the general result is Janicak's theorem. Actually, I've got no idea how to pronounce it, but it seems like it could be that. Janicak, Janicak, I don't know. I don't even know what country he or she comes from or came from. Don't know anything about them apart from that they have this theorem, actually. So the theorem is that if T, any theory T in a countable signature, that's being assumed, is computably axiomatization. So here we're going to use the notion of computable axiomatizability. If T is computably axiomatizable and complete, then T is decidable. So DLO is finitely axiomatizable, hence computably axiomatizable. So if we show it's complete, it will be decidable. And the proof of this is really easy. So the proof is that T is computably axiomatizable. We have that T is computably enumerable or semi-decidable. Same thing, semi-decidable by the previous theorem that was characterizing computable enumerability. Computable axiomatizability is equivalent to the theory being computably enumerable. So we just need to show by the proposition we had earlier on that if a set is decidable if and only if it and its complement are computably enumerable, we just need to show that T prime. We need that, sorry, T prime, that the complement of T is computable. So we need only show that the complement of T is computable. So given A, to semi-decide, well, let's put it like this. To semi-decide the complement of T, given input formula A, input sentence A, what we do, well, because the theory T is complete, remember complete for a theory means for every sentence A, either A or not A is in T. So to semi-decide T, given an input sentence A, well, the sentence A is not going to be in T if and only if the negation is in, if and only if its negation belongs to T. So we simply run the semi-decision procedure for T on the input not A. So if A doesn't belong to T, then not A will belong to T, and so the semi-decision procedure will indeed return, will indeed terminate with the yes, which is what we want. So that's it. Okay. So the remaining thing is to prove that, so I want to apply this to the theory of dense linear order. And so we now want to use model theoretic techniques to prove that the theory of dense linear orders is complete. And maybe just before the break, I will state the theorem we prove, because this is a really beautiful theorem. One of the contributions of Georg Cantor to mathematics, and in this case, it has nothing to do really with set theory. So it's a kind of sort of combinatorial kind of result, or some structural result. I'm kind of interested how many people have seen this before, actually. So this is a result now specifically if we want to prove that dense linear orders are complete. So let's consider some example dense linear orders. So actually, maybe this is a good point for some audience participation. Who can give me an example of a dense linear order?
The reals with the...
Okay, very good. The reals with the usual less than relation. Okay. Any others?
Whole numbers.
Sorry?
Whole numbers with...
The integers. Oh, but they're not dense, right? You don't have any numbers between 0 and 1. So the rationals. Okay, any others?
Can take like copies of the reals, this force one that's be bigger.
Oh yeah, we could do. We could take rationally many copies of the reals, for example. That would be what. I'm not going to put that one down. That's too complicated to write. Okay, David can. That's going to be the same as the reals. So one we've already considered. We mentioned before the algebraic numbers. Let me just mention another. I like to write it Q sub D. This is the dyadic rationals. So these are the rational numbers they can be written as integer fractions where the denominator, the thing on the bottom, is a power of 2. Okay. So there's a very interesting fact about these three structures that includes these three structures plus many others. Does anyone know what it is? Does anyone know what's the relationship between these three structures? They're all countable, indeed. I'll clear the board. I'm just wondering if anybody actually knows Cantor's theorem here. So I'm removing the axioms for dense linear orders, but I guess. So can anyone guess what it's going to be? Well, let me start it. All countable dense linear orders are. Can anyone guess what? There's one word to come here. Sorry?
Isomorphic.
Isomorphic. As ordered structures. It's not at all trivial, but I mean, these three structures are all isomorphic to each other. Notice we don't have the arithmetic, we don't have the operations, but we don't even have the number 0 identified. We've simply got the set and the order relation. And with the set and the order relation, they're all isomorphic to each other. So it's now exactly 10 o'clock, so we'll have a break until 1:15. But for those of you who like challenges, this is a beautiful result. It's not that hard, but if you'd like to think about something during the break, you can see if you can prove it for yourself. I mean, we'll have a proof at the start of the next hour, but it's a fun challenge. Right. Okay, so I'm pausing the recording. Okay, well, I don't know if anybody managed to prove Cantor's theorem for themselves. There are a couple of ways one can do it. It doesn't involve any complex analysis, but anyway, some people were thinking along sort of approximately the right lines in discussions I heard. So let's do the proof. So we just dive in and let's assume we've got two countable dense linear orders. So let x, and we'll give it less than x relation, and y, and less than y relation be countable dense linear orders. So we might write x. So x is countable, so maybe it's got elements. Let's enumerate its elements. And y is also countable. Of course, it's easy to prove, sorry, this should be a y. It's easy to prove that any two dense linear orders are infinite. I think that is an exercise. Trivial, basically. So certainly got infinite countable x and y. And we now want to construct a bijection between them. So this is one of these kind of nice proofs that it's easier to do with a picture. As long as you trust proof by proofs by pictures. So we've got X. So X is going to be some linear order on this countable set of elements. So for example, X0 might be here, X1 might be here, X2 might be down here, X3 might be down here, X4 perhaps is here, X5. I don't want to, you know, there are lots of elements to draw, so I'm not going to go very far, but you know, you've got some picture like this, they're all in a linear order, and the order relations between them are kind of higgledy-piggledy. And let's do Y in red. So Y is here, and so maybe we've got Y0 here, and Y1 might be down here, and Y2 say up here, Y3, Y4, Y5, Y6. Is that one? I don't know. Anyway, so what you do is there are a couple of methods, but the nicest one I think is to do what's called a back and forth construction. Back and forth. Forth means forwards. So what we do is we alternate between sides X and Y. You start, say, for example, with X. You pick the first element in the enumeration that has not yet been chosen, and you match it with the first available element in the enumeration that, well, the first element in the enumeration on the right that is suitable as a pairing for this one. So at the moment, anything is suitable. You'll see what suitable means. It basically means that we preserve the order with the, so we map X0 to Y0. So maybe I'll continue the proof in writing on the right-hand panel here. Let's just move the camera very slightly. So for stages, so basically we're doing it in stages. The stages n equals 0, 1, 2. So starting counting at 0, 3, 4, and so on. So at even stages, we pair the first available X element. So that means first means lowest in the enumeration, available X element with the first suitable available Y element. And at odd stages, we just reverse the role of X and Y. At odd stages, we pair the first available Y element with the first available X, with the first suitable available X element. So what does suitable mean? Well, so let's go to the next stage. So we've done the first stage with X, X0 gets paired to Y0. The next stage is we take the first element that's not yet been used, so that's Y1, and we pair it to the first suitable element. So that's X2 here, because that's because not the X1, because then we wouldn't be order preserving. So the point is we always need to find an element so that none of the lines cross. So Y1 goes to here. Now we go to the next stage. So that's on the left-hand side. So we do X. So X1 is the first element that's not been chosen, and that goes to the first Y element that's not been chosen. That goes to Y2. Go over to this side. We've now used Y0, Y1, and Y2. So Y3 over here is the first one that's not been chosen, and we find the first suitable element. So there's going to, this order doesn't have an endpoint, so there must be some elements up here. It's just not x, it's not x3, x4, or x5, or x6, because x6 happens to be somewhere down here. So actually the first suitable element in this case turns out to be x7. So that gets paired to this. And now the first suitable element on the left, we've used x0, x1, and x2. We haven't used x3. On the right, we've used y0, y1, y2, and y3. But the first suitable element down here is to pair x3 to y4. Over this element now, on this side, y5 can get paired to x. What on earth is this? Here we've got x5. Didn't have two x5s. This must be an x6. Anyway, you get the idea. You go back and forwards, and you can always. So here we've done. Okay, so here we'll just do one more. So now when we come to the left, x4 is the first suitable one. This needs to go somewhere between these lines, and by density, there is some yi between these points. So we apply by the density x, and there has to be something here. One of them will have lowest index. Actually turns out in this case it's y17, and we pair x4 to y17. And we keep on going like, so it actually looks like I've kind of almost completed. Oh no, anyway, you get the idea. And by the end, one has constructed a bijection between the two sides. And the reason for going back and forwards is that it's very easy to see that it's a bijection, because every element on the right-hand side, so for example, yn must have been used by the time we've done n moves on the right-hand side. It must have been paired with something. And xn must have been paired with something by the time we've done n moves on the left-hand side. So by this back and forth construction, we guarantee that we have a bijection. In fact, if you do just the first bullet point in all stages, it turns out that constructs a bijection. But the proof that it's a bijection is quite a bit combinatorially harder than proving that the back and forth construction is a bijection. So the back and forth construction is the nice construction of a bijection. Okay, so I hope that picture convinces you that they're isomorphic. So for those of you who are thinking about it by actually trying to, for example, explicitly construct a bijection between the rationals and the dyadic rationals, it's actually very hard to do that. The right way to think about it is in terms of enumerating through the elements. It's actually really hard to just work with these as the mathematical structures and find an order preserving bijection there. I mean, if somebody has a good way of doing that, I'd be interested to hear it, but not now. Right, okay, so we've got Cantor's theorem. All countable dense linear orders are isomorphic. What does this tell us? So as I said, we're aiming to prove that the theory of countable dense linear orders is complete. And actually, that's what it tells us. And that's by a very nice general result. So actually, maybe I'll do this on. There's an important notion in logic that applies specifically to theories for which all models of a certain size turn out to be isomorphic to each other. And such theories are called categorical in the size of the set in which all structures are isomorphic to each other. So this is the definition for a cardinal K, kappa. Now, you don't need to know what cardinals are in this course, but I'm just giving you the general definition and then we'll specialize it. But for those of you who do, a cardinal is a size of set. For a cardinal kappa, a theory T is kappa, what's called kappa categorical, if all models with underlying set cardinality kappa of cardinality kappa, all models of T, that is, are isomorphic. Okay, that's the general definition, but the important thing for our purposes that doesn't involve the general notion of cardinality is that we say that T is omega categorical. It should be aleph naught, but people always say omega categorical. T is omega categorical if all countable models are isomorphic. So Cantor's theorem, and I'll just put this one in a box because this is the one that we're really concerned with. So Cantor's theorem, reformulated, says that DLO is omega categorical. All countable models are isomorphic. And this relates to completeness. Because of the following result. Theorem by, I think this is Vaught. Yeah. If T has no finite models, and T is kappa categorical for some infinite cardinal kappa, then T is complete. And this is the general statement, but in this course, I just wanted to show you the general statement. In this course, we're not dealing with arbitrary cardinalities, so it's not, of course, about set theory and cardinalities. So I'm going to just immediately replace this with omega categorical, and that's the only version we're going to need. But before doing that, I want to just make a remark about that. This is actually a very important statement of the cardinalities. So there's a very famous example of a theory that is categorical in cardinality 2 to the aleph 0, the cardinality of the continuum, and that is the theory of algebraic closed fields of characteristic 0. That has only one model up to isomorphism of cardinality 2 to the aleph 0, and that, what is the algebraic closed field of characteristic 0 of cardinality 2 to the aleph 0? The complex numbers, of course. So any other algebraically closed field of characteristic 0 of cardinality 2 to the aleph 0 is isomorphic as a field to the complex numbers. And moreover, that's is isomorphic as a field to the complex number. That's a very deep result. And that result proves that the logical theory of algebraic closed fields of characteristic 0 is complete. and hence decidable because it has a countable, because it has a complete axiomatization. So that's probably get a very deep and important decidability result using 2 to the other theorem here. But for the purposes of this course, I mean, that's quite a difficult theorem, but for the purposes of this course, we're just going to have omega categorical in here, and I'm going to prove this. And once we've proved this, we've seen that dense linear orders are omega categorical, hence complete, and by Janicak's theorem that we had before, hence decidable. So this is the remaining thing we need to prove in our treatment of dense linear orders. Okay, so what we want to show is that T is essentially the theory of a single structure. It doesn't, you can basically choose any countable, countably infinite model, and T will be the same as the theory of that model. And hence it is then complete because the theory of a single structure is complete. So the way I've got this in my notes is that we're going to consider any 2 structures and show that the 2 structures have the same logical theory. Any 2 models of T have exactly the theories of those 2 structures are the same. So let M and N be 2 models of T. I'm assuming now that T has a countable signature, again, I've said that several times. So since it has no finite models, they're necessarily infinite. So by the elementary substructure theorem, we can find countable elementary substructures of them. Well, I was going to say and, but there's nothing else to say. We can find countable elementary substructures of M and N. So by the elementary substructure theorem, our version of the downwards, by the countable, as we called it, countable elementary substructure theorem, substructure theorem, there exist countable M prime and N prime with 2 elementary substructures of M and N. So M prime is when we use this kind of curly less than or equals. M prime is an elementary substructure of M, and N prime is an elementary substructure of N. So we have M and N. So M and N are both countable, and the theory is assumed to be omega categorical. So M and N are isomorphic. So we have M prime is an elementary extension of M, which is isomorphic to N, which is an elementary substructure of. Sorry, hang on. I've got it the wrong way around. M is an elementary extension of M prime, which is isomorphic to N prime, which is an elementary substructure of N. So the theories of all these structures are the same because they elementarily embed in each other. So the theory the same as the theory of M prime is the theory of N prime is the theory of N. So any 2 models, so if we fix the theory, if we fix the model M, for any other model N, it has the same theory of M. So all models, so in other words, T, so all models have the same theory, and since T is the theory of its set of models, by definition, so we have T is the theory of M. and hence, so T is the same as the theory of a single structure, and hence complete, because every sentence is either true or false in M, and hence complete. Okay, so we're done. I should say just one other remark, which I might use later. Another way of saying this line, which I haven't used this concept in the lectures, but probably I think Gregor might have used it in the exercise classes. So equivalently, a different way of saying that is to say that M is what's called elementary equivalent to M prime, is elementary equivalent to N prime, sorry, is elementary equivalent to N. Let me say two structures, M and N are elementary equivalent if they have the same theories. If the same sentences are true in each of them. Theory of M. Whenever you have an isomorphism or an elementary embedding between two structures, they're elementary equivalent. Right, okay, so that's dealt with the theory of dense linear orders. The last result I want to mention is going to be another decidability result. But again, this time a new one we haven't seen in the course so far, and again falling very nicely out of model theory. And again to do with axiomatizability properties. So the last one was a result about finitely axiomatizable theories that are complete are decidable. We're going to consider different, and in order to prove completeness, we proved this categoricity property, and it was important to get the completeness property that we were considering theories that have no finite models. We're now going to look, for the last part of the lecture, we're going to look at something that goes in a completely different direction, theories where having finite models is really important. And this is called the finite model property. So the definition is T has the finite model property if whenever a sentence A is satisfiable by a model of T, it is satisfiable by a finite model of, by some finite model of T. Whenever A is true in some model of T, is true in some finite model of T. And the reason this is interesting, we haven't really seen many examples of this kind of phenomenon because we've often been looking at theories that have only infinite models, like dense linear orders, but a lot of the theories we've looked at in this course have only had infinite models. But when you do have such a situation, then there's theorem by Harrop, which is that if P is finitely axiomatizable, and has the finite model property, then P is decidable. So this time, computably axiomatizable is not good enough. Finitely axiomatizable is. So there are two things to do. One is to prove this. Now, and the other one is to give an example. I think I prefer to do the example and then come back to the proof of this if we've got time. Just to say, just very briefly, the proof of this, T is finitely axiomatizable, so T is therefore computably enumerable, is semi-decidable by our result that said every computably axiomatizable theory is computably enumerable, is semi-decidable. So once again, we only need to show that the complement of T is semi-decidable. So given a sentence A, we need to find a way of checking if A is not a consequence of the theory T. Now, if A is not a consequence of the theory T, then the negation of A is consistent with T. So there exists some model for the negation of A together, some model of T that satisfies the negation of A. By the finite model property, there's a finite such model. So basically, to semi-decide whether A is not, to find out if A is not a consequence of the theory T, you consider the negation of A, you enumerate your way through all finite structures, you check if each finite structure is a model of T, in which case you use to do that, you use the finite model, the finite axiomatization of T, and you check if it satisfies not A. And if not A is not a if A is not a consequence of the theory, there will be some finite structure that satisfies not A. Eventually you will find it, and that's how the proof works. So those proofs, again, that proof's written up in the LaTeX notes. What I want to do is look at an example of this, because the example is quite a surprising example, because it looks very, very powerful, but it actually turns out to be less powerful than, I mean, it's a nice result, and it's a pattern for a lot of results, important results in more richer logics than first order logic. And this pattern is patterns to do with something called monadic logics, where we're going to consider what a monadic logic is and what monadic first order logic is. And the idea here is that this applies to logical theories where you only have unary predicates, so predicates that can only take one argument. And the result is quite surprising. So the example is what's called monadic logic. I think I need to move the camera. Oh no, I've moved the camera. Maybe I needed to move it before. But anyway, the idea of monadic logic is the signature is simply a collection of unary predicate symbols. So P1 to Pk are all unary predicate symbols. theorem is monadic logic has the finite model property. And by this, I mean the empty theory in monadic logic. So we have all structures, the theory of all structures for monadic logic. We've got some signature with k unary predicate symbols. And we just want to ask, we want to say, so the finite model property says, if A is satisfiable, then in any structure for this signature, then A has a finite model. So it's true in some finite model. Its consequence, we get that monadic logic is decidable. And namely, the validity of sentences in monadic logic is decidable. So whenever you have a logical sentence that involves only unary predicates, there's an algorithm to decide if it's valid or not. So it's kind of surprising because you might imagine that you can express quite a lot using unary predicates. Like the predicate is mortal, or predicate, the kind of thing Socrates used to talk about, or Aristotle used to talk about. Sorry, Socrates is mortal, and this kind of thing. But if you look back over all the interesting example theories in the course that we've considered, you will find that all the interesting example theories we've considered in this course have either used a binary predicate or a function symbol in them. So this is just unary predicates only, and in a sense with unary, that's not quite true. We had the theory of the empty signature at the start, and that was already quite interesting enough. So this is actually a result that generalizes the decidability of the theory of the empty signature. We don't just have the theory of the empty signature is decidable, but the theory of whatever we can say using any number of unary predicate symbols. Right. Okay, so the remaining thing to do in the last 10 minutes is to prove this. I feel like a change of colour at this point, so let's get. So the first main lemma we use is, well, actually, before putting the lemma, so what it turns out to be the case about this kind of signature, so we have a very good handle on structures for this signature. So for any L structure, this signature we'll call L, and for any L structure M, we define what I'm going to call the characteristic function of M. And this is going to be a function from power set of the indices of the predicate of the k predicate symbols, so from 1 to k, to natural numbers together with infinity. And the definition is characteristic function of M applied to a set of indices of predicate symbols is simply the size of the set of X belonging to the underlying set of the structure M, such that the predicate symbol interpreted in the structure M applied to X is true if and only if is the predicate symbol for something in the underlying in the index. So what we're looking at is the set of all x that satisfy exactly the predicates pi that belong to the index set I, but none of the other predicates. Okay. And this bar here, it's kind of like cardinality. It means the cardinality if it's finite. So if it's a finite set, then we assign a natural number. And if it's an infinite set, we just assign the value infinity. We're not going to be bothered about distinguishing between different infinite sets. Okay, so for every set of predicates, for every set of indices of predicate symbols or labels of predicate symbols, we look at the number of elements of the structure that satisfy exactly those predicates, but none of the other ones. Okay. And the lemma we have concerning this, maybe I can squeeze it at the bottom of the board, is that if M and N are countable L structures, then they're isomorphic if and only if they have the same characteristic functions. And only a characteristic function of M is the characteristic function of N. So this, for countable structures, this characteristic function characterizes models, characterizes structures up to isomorphism. Okay, it's not that hard to prove that, so I won't prove it. So this is the kind of the proof of the main theorem is sort of proof that one divides into lemmas, each of which takes a bit of work to prove, but somehow they're almost self-proving. You just need, if you think about that, you'll find that it's easy to prove that. It's more just a problem how to write it down. So the second lemma we need so let's call this one lemma A. The second lemma we need is lemma B. We define actually before lemma B, we need to make another definition. The point is I can now code up these structures by a logical theory. I'm going to define the sentence char for characteristic I greater than or equal to n. I'll write it like this. And this is the sentence that are going to say that. So this is for any define for any I in the power set of, so any I that's a subset of the set 1 to n. This is going to say, it's going to be the sentence saying I am true in a structure whose characteristic for I for the index set I is greater than or equal to n. So we can easily do this using a kind of modification of our cardinality sentences. So our cardinality sentences were from saying that there exist x1 to xn, which are all distinct. So that was that. We're going to add to this. In addition to this, there exists x1 to xn that are all distinct, and they satisfy and each xi satisfies exactly the predicates in I, but not the predicates not in the index set I. So from I, so for all the little I in the index set, this should be, I realize I've got, this should be for all I from 1 to n, and for all, I'm mixing up my indices here, so let's make it j from 1 to n, and for all I in I, p I of xj, and for all j, for all j from 1 to n, and for all I not in I, in the set 1 to n minus I, we have not p I of xj. Okay, but it's saying we've got at least n distinct elements that satisfy exactly the predicates in the index set I and none of the predicates not in the index set I. And going to define P substructure to be the theory of saying that car I is greater than or equal to n for all I and n such that the characteristic function of the structure of I is greater than or equal to n, and the negation of these in all the cases where the characteristic function is less than n. And the lemma here is that if m and n are countable L structures, then the point of this theory, so this should be Gm. The point is this theory characterizes the structure up to isomorphism. Okay, well, it's 11 o'clock, so let me tell you. So I've always struggled with this lecture in the past when I've given the course, and I never managed to squeeze this proof that monadic logic is decidable into the lecture. And so today, I sort of reshaped things a bit in the idea that I would be able to shoehorn it. You know what a shoehorn is, for squeezing your foot into a shoe. Shoehorn it into the last however many minutes of the lecture, but I obviously didn't quite get it right, and I've already been rushing on this part. And we've still got the main bit of proof to come, so I'm basically not going to manage to do it. So what I regret about this is I always thought it would be a beautiful thing to have this particular proof examinable. From my side, the beautiful thing, because I think it's a really nice proof. But given that I haven't managed to squeeze it into the lecture, what I will do is I will put the notes up online, but I feel it would be unfair to you to make it examinable. So I'm afraid you will have to accept the situation that this particular proof will not be examinable. But nonetheless, it's a lovely proof, and I wasn't doing it justice because I was rushing at the end. But if you've got 20 minutes to spare over the next week, then I kind of recommend you. Well, actually, you're going to do something in the exercise class tomorrow that will build off this proof. So So in any case, you will kind of get acquainted with it in that way. Anyway, sorry for not being quite managing to fit everything in today. That's it for today. So have a nice week and see you next week.